Hi, Charles. Would you be able to give a simplified version of how proof of stake works? Yeah, sure. There's a very easy way of thinking about proof of stake. So, both proof of work and proof of stake are attempting to achieve the same thing. So, all the old consensus algorithms, the RAFs and the Paxoses and these BFT protocols, basically they existed with an assumption that you have a static and federated system. Static in that you're not going to change your consensus set very often, and federated in that set is basically a set of actors, so 5 or 7 or 9 or 11, and it's not elastic, so it doesn't go from like 7 to 30 or something like that. Now, this was built because at the end of the day, you were talking about computers amongst known actors who basically own the hardware, and they're building a distributed system to optimize. So you're going from one computer to many computers. Byzantine resistance was added because maybe you're doing things where hardware is unreliable, in which case it, by no fault of its own, gives you wrong answers, and the system needs to be self-correcting. You don't want to halt as a consequence of a bit being flipped, or because you're actually networking with outside parties. But you still have a situation where the system is, for the most part, static and federated. Now, we're moving to a dynamic and decentralized system. Dynamic in that lots of people can join, and you don't know how big that set's going to be. And basically anybody can play. You don't need permission to play inside the system. So this requires a new class of protocols, and the first of its kind was proof of work, and then proof of stake was invented thereafter. The big difference is that you need some sort of resource to determine participation. And so in the case of proof of work, your resource is hash rate. In the case of proof of stake, your resource is ADA. Now that resource, then you can make decisions about who gets to advance the system. So basically you can think of it this way. You have your system in state A, so whatever today's state is, so the current set of all the values. And then you run it. And then a lot of people propose things. They say, okay, I want to send this amount to Bob, and I want to send this amount to Eve, and so forth. And those are called pending transactions. And they go ahead and sit in a memory pool, and they just wait for somebody to bunch all of them together, make a block, and then advance the network to the next state, the state B. Okay, well, what proof of work and proof of stake is all about is it's a decision mechanism to decide who gets the right to bundle all of those things that are sitting in the memory pool together and advance the system from one state to the next state. Then that candidate is broadcasted throughout the network. And if they follow the rules, all the validating nodes, all the full nodes in the system can look at that and say, yeah, that looks good. I accept that block. So basically there's a select who's going to do it, and then check the work of the person who does it. The only major difference between proof of stake and proof of work is that in proof of work, the selection phase is basically a lottery system determined by hash rate. So you basically, a lot of people are buying tickets, all their mining capacities, how many tickets per second they can buy. So you have a gigahash, you can get 1 billion tickets per second, you have petahash, et cetera, et cetera. And basically, at some point, you find that lucky ticket, that lucky hash that is a winner, and then that, if you're fast enough, can be used to go ahead and advance the system. You get the right to do that. Now, if two people roughly the same time get winning tickets, then you actually have a fight between them. And then the first person to have somebody build a block on top of their chain is the winner, and then the other one actually gets discarded. That's called an orphan block. Now, with proof of stake, what we do is we say, instead of using hashes to do this, we say, okay, we're just going to synthetically let people win. So if you have 25% of the ADA in circulation, 25% of the time, on average, you'll have a chance to win. And with a delegation system, you can take that and give that chance to win to a stake pool operator on your behalf. And then they go and participate. But the only way you get paid is by actually making the block. This is one of the reasons why it's not right to call proof of stake like interest or a dividend or something like that. Because with interest and dividend, you have a legal right to a payment just by holding an asset. With stake, you don't. You actually have to do something. You have to either do it yourself, or you have to entrust somebody to do it on your behalf. And they actually have to go and do that. And what they're doing is actually real utility for the network. because if these stake pools didn't exist, well, then the network couldn't advance. So the network as a whole is paying people to do something, and the only way they can do something is by participating in this synthetic lottery effectively, and actually then constructing the block and advancing it. So it's a pretty clever system because you achieve open participation and you achieve decentralization. But unlike Bitcoin, because you're not spending any electricity on that synthetic lottery, basically you have a constant amount of power that's being used, very, very small amount. In our case, about 10 kilowatts if we had 1,000 stake pools and they were all running Rock Pis. So what does that mean? Like for the power of a large home, you can run a global scale financial system. Whereas Bitcoin, the problem is that as the cost of energy goes up, the hash rate goes up, and the value of Bitcoin goes up, you're going to use more and more and more electricity to stay competitive for those same amount of coins. So as a consequence, there's no incentive to reduce power consumption in the system if the system becomes more valuable. It's quite the opposite. Anytime the value goes up, you will spend more and more electricity to acquire that value. So this is what's made Bitcoin go from the power of one laptop to the power of an entire country like Switzerland. And if Bitcoin continues to grow like to $1 trillion market cap, it will consume more electricity than Canada. It'll consume more electricity than Argentina, very large countries. So it does give you a sense of how problematic this will be environmentally speaking. And all of that is totally eliminated with proof of stake. As with all things, you talk about trade-offs, and the trade-offs are that you have an endogenous resource versus an external resource and an exogenous resource. So they have different trust models. An exogenous resource is a resource outside of the system. An endogenous resource is a resource within the system. Okay, so a resource outside of the system means that you are trusting a process that lives outside of your protocol to make the protocol secure. So you are relying on mining hardware existing, people using that mining hardware, and for a sufficient amount of it to be around that it would be quite expensive for the system to be hacked. In the case of an endogenous resource, you're saying that something within the system, a resource that exists within the system, is what gives the system security. So the more expensive that resource happens to be, and the more plentifully distributed that resource happens to be, then the less chance you have of fraud and abuse of the system or damage to the system. So you have a direct alignment with an endogenous resource to the financial incentives of the system and security and health of the system, whereas you do not have a direct alignment with an exogenous resource, because that mining capacity could be used for any proof of work coin that shares that same hash power. This is a big difference between the systems. Even if there was an ADA Classic, the ADA in ADA, regular everyday Cardano, cannot be used to secure ADA Classic. So whatever value of one system can't be reused to the other system. But if you had a Bitcoin and a Bitcoin Cash situation, because they both share the same consensus algorithm, a miner chooses to either mine chain A or chain B. Here's the problem with that. If chain A and chain B have roughly the same hash rate and the same value, the miners of one of these chains actually have an incentive to collude and destroy a chain and then move all hash power over to the other chain, because they can maximize profit. You can't dilute your resources. If you mine A and B at the same time, you can only split your resources 50-50. So you'll make roughly the same amount of money. But if you destroy one of the coins, you can use financial products like short selling and derivatives, these types of things, to make windfall money as it's in free fall, because it becomes unusable and it's broken. And then when it's destroyed, you just move all your hash power over to the other system, and you'd make the same amount of money if you mined A all the time, but you get to keep all the value of destroying A. That's the problem with proof of work, is it's a winner takes all type of system, and it's very mercenary. And so if you're defending your city with mercenaries, you have to be very careful, because those mercenaries may have an incentive to turn on your city and sack it if someone pays them more, or if they realize that they can get away with that. Whereas an endogenous resource is like defending your city with your own people. You know, if they turn on the city, they're killing their kids, they're killing their family. So that's really the big difference philosophically between these two things. But to get proof of stake to work in principle and synthesize all the security properties of proof of work, That's super, super, super hard. And that's why we've had to spend years and years of research to understand, can we do this synchronous or asynchronous or partially synchronous? Can we get adaptive security? Can we bootstrap from Genesis? There were a lot of properties that proof of work gets for free as a consequence of its design that are really hard to emulate with proof of stake in a provably secure way. So that's why we had to write a lot of papers and spend years thinking about it.